is Chapter 9.1, the basics of hypothesis testing. So hypothesis tests or significance tests really mean the same thing. A significance test is a formal procedure for comparing observed data with a claim, also called a, guess what, hypothesis. Whose truth we want to assess. There's two types of hypotheses in statistics. The first one is the null hypothesis. The claim tested by a statistical test is called the null hypothesis, and you denote that with this H with the little 0 called H naught, or the null hypothesis. The test is designed to assess the strength of the evidence against the null hypothesis. So it's kind of counterintuitive at first because you're actually trying to build up enough evidence against the null hypothesis so that you can show evidence for the alternative hypothesis. Usually the null hypothesis is a statement of no difference or just the status quo. Then the claim about the population that we are trying to find evidence for is called the alternative hypothesis. And you can see that that is denoted with a little a subscript on the H. Since the null and alternative hypotheses are both referring to a population and not a sample, when you state them, you're going to be using the population parameter symbols. So either mu or p. There are two possible types of tests. You have one-sided alternative hypotheses or two-sided alternative hypotheses. The alternative hypotheses is one-sided if it states that a parameter is greater than the null hypothesis or if it states that it's less than the null hypothesis. So it's just one direction either way. So it's either greater than the null hypothesis value or less than the null hypothesis value. It can also be less than or equal to or greater than or equal to, but normally it's just less than or greater than. The two-sided tests or two-tailed tests, sometimes they're called, states that parameter is just not equal to. So it could be bigger than, it could be less than. We just know that it's not equal to, and that's denoted with an equal sign with a line through it. Okay, and that would be a two-tailed test. You'll be seeing more of these later. So the bread and butter of statistics is called the p-value. If you understand statistics at all or do any type of analysis with statistics, p-value is your payday. You're going to be using p-values to show that you have evidence against the null hypothesis. It'll become more clear later when we start doing more analyses, but the p-value is the probability computed assuming H naught is true that the statistics such as p hat or x bar would take a value as extreme as or more extreme than the one actually observed. That's called the p-value. The lower the p-value or the smaller the p-value, the stronger the evidence against H naught. So for example, when we were talking about can Joy smell Parkinson's, we assumed that she couldn't. So we were assuming our H naught was that the probability of her actually being able to choose correctly was just a 50-50 chance. Now our p-value, when we did some of the simulations, ended up being very low. So against the alternative hypothesis was actually that she could do better than 0.5, that she could actually smell Parkinson's. So when we did our simulation, we got a p-value, which was the probability that, assuming she can't smell Parkinson's, what's the probability of getting 11 or 12 out of 12? And we ended up in our simulation with getting a basically 0.0036. So that's highly unlikely that she was actually just guessing. So that was a very low p-value, and that's strong evidence. So the lower your p-value, the stronger your evidence. So when you're doing statistical analysis and significance tests, you have two choices depending on your p-value. You can either reject the H-naught if the data gives convincing evidence against H-naught, or you can fail to reject H-naught. Notice we never say that you're accepting H-naught. You're just failing to reject it. So it doesn't mean that H-naught is true if you don't have enough convincing evidence. It just means that I don't have enough evidence to go against H-naught. So if I fail to reject H-naught, if the data does not give convincing evidence to support HA, and we fail to reject H-naught, we can also abbreviate that FTR, fail to reject. So the question is, how much evidence is enough? Well, it depends on what the statistician sets as their sort of litmus test for what would be enough evidence. So you choose something called an alpha level. Normally, we would default to an alpha level of 0.05. So if a problem does not give you an alpha level, start with an alpha level of 0.05. The alpha level has to be chosen before you do the statistical analysis. If you choose your alpha level after, that's cheating because you're basically deciding on an alpha level after you've already done the analysis. You can't do that. You have to pick your alpha level first. If your p-value ends up being less than your alpha level, we say that the results of a study are statistically significant. At level alpha. So to kind of summarize, if your p-value is less than alpha, that is good, strong evidence, and we reject H-naught. If your p-value is greater than or even equal to alpha, we fail to reject H-naught. So the bigger the p-value, the less evidence against H-naught. The less the p-value, the more evidence against H-naught. So we did an example talking about jury trials. So there are two types of errors you can come up with as a statistician. If you reject H-naught when it's actually true, and I shouldn't have rejected it, that's something called committing a type 1 error. If we fail to reject H-naught but it was false, then we've committed a type 2 error. So putting this in the context of courtroom cases, say I have a defendant that is actually innocent. So remember, we assume innocence, and we have to prove not innocent or prove guilty. So if the defendant actually is innocent, but I reject the idea that they're innocent, then I've committed a type 1 error, and I've put an innocent man in jail because they were actually innocent, but I rejected that idea. Now, if they're actually innocent and I fail to reject that innocence, then I've made a correct decision and everybody's happy. Now, what if the defendant is actually guilty? So if the defendant is actually guilty and I reject their being innocent, then I've made a correct decision. I rejected their innocence and they were guilty, so therefore they go to jail, and a guilty person's in jail, so everybody's happy. Well, maybe except the guy who's in jail. But the right decision was made. If the defendant's guilty, but I fail to reject them being innocent, I've created a type 2 error, meaning that I've sent a person that was not innocent free, and I failed to reject that they were innocent, and therefore I've made a type 2 error. So a couple different movie and real life scenarios. If you've ever watched Shawshank Redemption, that was an innocent man that went to jail. If you haven't watched it, you should watch it. Look it up. Type 2 error would be OJ, because unfortunately he got set free, and we all at this point in time know that he was guilty. So those are called type 1 and type 2 errors. So in statistical analysis, the type 1 and type 2 error is the same idea. If the null hypothesis is actually true, but I reject, then I've made a type 1 error. If the null hypothesis is true and I don't reject it, that's a good decision. I made the right decision. If the null hypothesis is false, but I reject it, I've made a right decision because I should reject it if it's false. But if it's false and I fail to reject it, I've made a type 2 error. So later on we'll discuss more about the difference in the errors and which one is worse. But really it just depends on the context of the problem. And as a statistician, you have to decide, am I more worried about making a type 1 error or a type 2 error? And that way you have to adjust your alpha level and do some different things.